I think we're getting underway. So, hello everyone. My name is Russell Keith-Magee. If you have heard my name before, it's probably because of my work on the Django project. I've been a member of the Django core team for almost 11 years now, and I was president of the Django Software Foundation from 2011 to the end of 2015. Django has been around for just short of 11 years. Django and the web are still very important platforms. They're not going anywhere. But over those last 11 years, we've seen the emergence of a new type of platform, the mobile platform. Delivery of web content for a mobile form factor is one approach, and this is something that's evolved over time. But mobile platforms also offer a completely different way to deliver content to users as native applications. Now, it's no secret that the mobile space is dominated by two major players, Android and iOS. Unfortunately, Python hasn't historically had a very good story on either of those platforms. If you wanted to write mobile applications for iOS, you either had to learn ObjectiveC or, more recently, Swift. Then, to write your companion Android application, you had to learn Java and a completely different set of APIs for Android. There are a couple of other options using other languages, C#, JavaScript, even Ruby, for varying degrees of cross-platform and native, but Python was, for the most part, absent. It wasn't completely absent. Kevvy has been working in this space for a couple of years, but those tools are very much wrapped up in the Kevvy toolchain rather than being something generic you could use without Kevvy very easily. Over the last 2 years, I've been working on rectifying this situation. And the purpose of this talk is to show you what's currently possible and to give you a dive into how some of those pieces work to deliver a Python on mobile experience. Now, the first thing I want to address is exactly what I mean when I say mobile Python. Other people may and do have completely different interpretations, and they're all completely valid, but I have a very specific definition that I'm working for, which rules out certain options. When I say mobile Python, I'm talking about the development of a native application delivered as a native application using system native APIs. Let's break that apart. I'm talking about native applications. I'm not talking about HTML5 apps that are delivered using Python. I'm not talking about a native shim that displays a web canvas that then renders content generated by a client-side web server. I'm talking about an app that you start the same way that you start any other app on your device that behaves the same way as any other natively developed app would behave. I'm also talking about apps that are delivered using the normal platform mechanisms, downloadable as a single bundle from an official app store. I know you can jailbreak devices, and those approaches do open up all sorts of options. But an ecosystem that relies on jailbreaking won't ever really go mainstream. You can also do some really nifty things with system services on Android or treat the Android platform as a low-powered Unix server. I'm not talking about that sort of thing. I'm not targeting that space. I'm talking about developing and deploying apps with the potential for mainstream adoption. Essentially, at the end of the day, the end user should not know or care that the app they're writing or the app they're using was written in Python, any more that the users of Instagram and Discuss know that the websites they're using are written using Django. If they need to know or care, then in my opinion, you've failed. Lastly, the apps need to use native system APIs. The apps should look like native apps, feel like native apps, and behave like native apps, providing access to any native service that the platform provides. Using Python shouldn't be a constraint on your options in terms of what you can achieve. Okay, so given that definition of mobile Python, what is currently possible? Well, the short version, you can write a native iOS application, you can write a native Android application, and you can write cross-platform applications that target both of them. So let's start with iOS. We're going to start with iOS because it's actually the easier of the two to get going. It's easier because the toolchain you use to develop native iOS applications is Clang, which is the same C compiler that you use to compile CPython for a Mac. Now, that doesn't mean that iOS is just a POSIX. It isn't quite that simple, but it's fairly close. Close enough that with a few patches and disabling a couple of modules in the standard library, you can compile CPython 2.7, 3.4, 3.5 sources so they can run on the iOS simulator or on an ARM v6, ARM v7, ARM v7s, or ARM 64 or ARM v7K processors, which pretty much covers every hardware device that Apple has sold over the last 5-10 years, 5 years at least. Now, a patch to do this has been submitted for inclusion in CPython. It's issue 23670 on Python's bug roundup. There are a couple of design decisions that still need to be ratified. And there's an issue with the build system that was introduced in 3.5. I think it has been addressed in 3.6, but I still need to confirm that. But ultimately, merging this patch is just waiting for the attention of a champion within the Python core team. If that was done, iOS would be a fully fledged platform supported by CPython. And in the meantime, there are external compiling tools to let you get that patch and get a working version. Okay, so how does it work in practice? Well, you don't have a command line where you type Python -m myapp on an iPhone. So how do you use CPython on iOS? Well, you treat it like an embedded application. You write a very, very small C stub with a main line that starts a CPython interpreter as an embedded library and then starts the iOS event loop. Now, I could dig into detail about how you write that shim, but honestly, there's no point. Firstly, because it's pretty much the vanilla usage of embedded CPython, and the CPython docs actually do a pretty good job of explaining what you've got to do there. But also because, frankly, it's just easier to template it because every single app's got exactly the same stub. Python iOS template is a cookie cutter pattern that you can use to generate an entire ready-to-run iOS project. If you run cookie cutter over the template, you download the precompiled Python iOS libraries, drop those libraries into your project, and you're off and running. Full instructions are on that page, and you can take it from there. Once you've got your stub project, you're actually going to want to do something. Now, okay, you could start by writing hello world, but that's not going to be especially enlightening because it's just going to output its content to standard output, and your iPhone doesn't have a standard output, or at least not one that you can see. You can see it if you plugged into Xcode because it comes out in your console, but that's not an end-user user interface. What you really want to do is invoke some native iOS APIs. So how do you do that? Well, iOS native libraries are provided using Objective-C, which is a quirky language, but the good news is it's actually really, really compatible with Python. Quick aside here, Apple threw a little bit of a spanner in the works a couple of years ago when they announced the new language called Swift. The good news is nothing seems to be changing from Python's perspective. Swift looks really interesting, but to my read, it's ultimately just a really nice set of syntactic sugars around the Objective-C runtime, replacing the quirks of Objective-C syntax with some dynamic conventions that would be familiar to Python developers. And there aren't any signs that Objective-C is going away. And even if it did, Swift is built on top of the Clang toolchain, so there's probably going to be a way in somewhere. All right, so back to Objective-C. Here we've got some example Objective-C code for creating a URL object. The syntax, if you've never used Objective-C before, yes, it's extremely odd. But what we're saying here is that we want to pass the URL with string message to the NSURL class, providing an argument, which is a native Objective-C string. The string is annotated with the @ symbol. The string is going to be http://pyb.org. We're going to pass that as an argument in with the message, and what we're going to get back is a pointer to an NSURL object. How do we do this in Python? Well, the thing is, Objective-C, for all of its quirky syntax, is actually designed as a thin syntactic wrapper around raw C. All that quirky syntax is literally a translation to raw C API calls. So let's roll this out a little bit more to make it a little bit easier. The @ symbol is a syntactic shorthand for constructing an NSstring object. So we do that manually. NSstring alloc is the equivalent of a new, create some memory, or allocate some memory, and then we tell it we want to invoke a specific constructor, the init with characters of length 16. We pass that information in, we get back an NSstring instance, which we can then pass into our URL with string modification. Now, at this point, we're down to raw method invocations and C constants. So let's translate that into the raw C API. This is exactly, and I do mean exactly, the same code written in raw C. Get a reference to the class with the name of NSstring. Find the alloc message on, or the name alloc, which is used as a message. Send the alloc message to the NSstring class, and that gives you back an str object. Call the selector, the init with characters length selector, and pass that to the string object with the arguments http://bytecode.org and the length 16. And then you do the same thing again for NSURL, and what you end up with at the end of the day is a URL object at the end, which is a constructed URL, done entirely in raw C, but done inside the Objective-C runtime. Okay, that's raw C. How do we get to that from Python? Well, part of the CPython standard library is a package called Ctypes. Ctypes is a library that exploits the fact that the C calling convention under the hood is a very well-defined way to invoke C libraries directly rather than having to write a C module to access the functionality in that library. So using Ctypes, all you have to do is reference the name of the library, describe the prototype of a C method that you know to be in that library, and then you can invoke that method directly from Python. So, in this example, we're using Ctypes to load libc. That's the standard C library on POSIX boxes. We tell that library that there is a function in that, so we tell Python that there is a function in that library called structure. It takes a character pointer and a character as arguments, and it returns a character pointer. And then we can just invoke that method, libc.structure, passing in 2 bytes, we get back the string that's returned. Now, there's no need to compile anything to make this happen. Okay, there's no compiled artifact here, there's no writing a C module, you're just using the C calling convention to get into that function call. So if you can invoke C libraries directly, that means you can invoke Objective-C directly. So you take the very first call to get to the get the NSstring. We can load the Objective-C library, tell that library that there is a function called Objective-C get class that takes a character pointer and returns a generic object pointer, and invoke it. And then you get back a pointer to the NSstring class that we can use in subsequent calls. Okay, that's neat. How does it help? Well, Python is also a very dynamic language, and most aspects of the language runtime can be configured and overridden, including basic things like attribute access. So if you define a class with a dunder getAttr method, any attempts to access an attribute of that object will be turned into a call on that, to that dunder getAttr method. Similarly, for attempts to set an attribute using the dunder setAttr method. And we can use that to our advantage. If we've got an Objective-C instance and somebody invokes .something on that instance, I can use that as a trigger to do a lookup on the Objective-C API, find a selector that matches, retrieve an attribute with that selector. Python also allows you to intercept the process of invoking a function. If a class implements dunder call, that'll be used when someone tries to invoke a function on the invoke an object as a function. And again, we can use this as a trigger to invoke the underlying Objective-C method. Lastly, Python gives you the power to control the process of object construction. Everybody knows about dunder init, it's the object constructor, but there's also dunder new, which can be used to control the process of instantiating instances. And we can use this to bind a Python instance to a specific Objective-C instance. Pull that all together, and what you end up with is this thing called Rubicon. It's a library that gives you transparent Python-side access to the entire Objective-C runtime. Any published iOS, or for that matter, OS X or Next Step API, is now fair game. Now, there are some others in this space. If you hunt around for PyObjective-C and PyObjects, you'll see very similar processes. The difference for me is that Rubicon will work on both iOS and mobile, and it has absolutely no compiled component. Now, using Rubicon, accessing Objective-C objects becomes just as simple as loading the foundation libraries, getting a representation to, for example, the NSURL class, and invoking a method on it, with a slight conceit that every colon in a selector in that Objective-C, wonky Objective-C syntax, is being replaced by an underscore. So there's no background knowledge in Rubicon that knows what an NSURL is. It's being dynamically generated based upon the fact that you're telling it to invoke URL with string. You can even extend Objective-C classes in Python space and declare methods that need to be exposed in the Objective-C environment. You just need to decorate them to let the type construction process that the method needs to be registered with the Objective-C runtime. And this is useful when you're defining callbacks. But wait a moment, Objective-C is a C, so it's a typed language. How do you represent that typing information? Well, you can use Python 3's type annotations. You notice that poke with value method at the bottom. We've decorated it to say it's an Objective-C method. It needs to be exposed into the runtime. But its V argument is annotated to say it's an integer. And its return type is a none. What we're saying there is that poke with value is a method that takes an integer and returns a void. So you can use that information to do the type checking and the type conversions that are necessary to invoke it as an actual Objective-C method with typed information or with typed data. And to be clear, this is not a custom language extension. It is completely legal Python and has been legal Python since Python 3.0. It's just a slightly off-piste usage of the type annotation system. From here, it's just a matter of defining the right classes and invoking the right iOS methods. But you can use any iOS textbook guide to guide that process. Stick the code into the cookie cutter template and you've got a working, pure Python, completely native iOS application. All that's left is to submit it to the App Store and, well, profit, I guess. So, that's iOS. But what about Android? Well, on Android, the native compilation toolchain is Java, although based upon the US court cases, no, it isn't, I think. It's not the Sun, regardless, it's not the Sun Oracle VM, and that's the key thing. It's Java bytecode that is then compiled to an internal system-native format. You can still call system-native code, though. Java provides JNI, which is the Java native interface, which allows you to call compiled code from within Java. So you can just compile CPython and link it as an embedded library, right? Well, yes and no. You can do it. There is a separate ticket, 23496, trying to get a patch for CPython that does exactly this. Javier de Gaia has got a fork of Python 3.5 that compiles for Android devices. And this is the general way that Kevvy provides Android support as well. But there's a very big caveat on this. On Android, you can't use the Ctypes trick because the native libraries aren't exposed as C functions, they're exposed as Java APIs. And in order to have native widgets and access native APIs, you need to bridge between CPython and Java using JNI. And if you're using desktop Java, JNI is pretty efficient and doesn't have any serious constraints. But on Android, there's a hard limit of 2,000 object references that is hard-coded into the kernel. And on some devices, it's hard-coded even lower, and the only way you can find out what the limit is by falling over it when your application runs. And you need a reference for every data type, method name, and object instance that you reference in your code. To start Hello World and fully instantiate all the classes that are involved in Hello World for an Android application, you need 4,000 references, which is twice as many as the kernel hard limits you to have. So that means you've got to do a lot of reference caching and recycling, which means there's a lot of repeated lookups, and the lookups themselves are really slow enough that, to my mind, it probably isn't viable, at least if you're going to be using a lot of system native calls. All right, so this is Java, so we can just use Jython, right? Well, no, it's not that simple. First off, Jython only hit Python 2.7 support last year, so out of the box, you're already missing a lot of stuff. That may not be a major problem, but it's worth considering. Secondly, Jython actually won't compile for Android because it has a bunch of dependencies that aren't Java native. They've actually got some C-compile stuff in there anyway. And lastly, what you get with Jython is actually a fully functioning Python parser and interpreter. And as you might expect, this is not a small chunk of code. But unlike a desktop platform, it's code that has to be duplicated on every install because there's no system directory where you can install Java and then everything that uses Java can run it. Or use Python and needs to run it. You have to include it in your application. Every application needs to have it. So is there another way of handling this? Well, yes, there is. Let's take a simple Python function. It sings you a little song. When you run this program, Python parses and compiles this code into bytecode. Bytecode is a little bit like high-level assembler. It's a stack-based machine with basic primitives pushing and popping information onto a stack. Python then gives you the tools to inspect that bytecode. The dis module allows you to disassemble any function, or class, or whatever, into its bytecode representation. And if we run dis over our sing method, what do we get? Well, you get the raw bytecode instructions. Each of these is encoded in the PYC file in a binary format. This is the human-readable, decompiled version for you to look at. But hopefully it makes some sort of sense. We're going to configure a loop, set the bounds of the loop. We load a global symbol called range. We load 3 constants onto the stack, 100, 0, and -1. And then we invoke a function with the 3 positional arguments that are the most recent arguments pushed onto the stack. So that's range, 100, 0, -1, and so on and so on. Okay, that's nice, but so what? Well, let's do the same thing for Java. Here's the same code. We compile this with Java-C. We get a sing.class file. And if we look at the class file, what do we see? You see bytecode. Now, okay, it's different bytecode to Python's, but it's stack-based, and there's a lot of commonalities. You load and store variables, you set get symbols, push constants, invoke methods. So if they're both bytecode and they're both stack-based, can we convert from one to the other? Yes. Vaak is a tool written in Python that can convert Python 3.4 bytecode directly into Java 6 class files. When you end up running your output class file, it's not a Python class being interpreted. It is indistinguishable from a Java class. And that means you can bridge seamlessly between them. You can reference Python classes in Java and vice versa. There are a couple of small caveats on that, but for the most part, you just write your Java code, but in Python. So, again, you take your standard textbook Android API, render them into Python, compile to Java, and again, profit, I guess. Here's a snippet of some Android code setting up a main activity. We are saying our main activity extends android.app.activity. We've got an onCreate method. The second argument, state, is typed. It's an Android OS.bundle, and it returns a void. We have to invoke super, and then we can call on the log method myapp with a context of myapp, create new app, and then instantiate, list view, and so on. This is, if you go and get Hello World as an Android application, that is what the code looks like, except that now you're writing it in Python rather than in Java, and it compiles to a Java class file that's completely equivalent. As with iOS, there's a bunch of Android housekeeping that needs to get this, that's needed to get this eventually running, and there's a cookie cutter for that too. Run cookie coder over the template, download the precompiled Python Android support library. It'll even manage compiling the Python code to Java and packaging it as needed. And again, full instructions on that GitHub page. Okay, so far we've been able to write a native iOS application using iOS APIs. We've been able to write a native Android application using Android APIs. Can we do this cross-platform? Can we write our user interface code once and have it render on both platforms? Well, again, yes. One approach I've mentioned previously is Kevvy. Kevvy doesn't use native widgets. It treats the phone service as a canvas and draws it onto that canvas. For me, though, that's not really a satisfactory result. There's a bunch of reasons for that, and that's why I've been working on a tool called Toga. Toga is a cross-platform widget toolkit that uses system-native widgets. I started on desktop platforms, but I've been focusing on mobile recently to provide a compelling reason to give a damn about yet another widget toolkit. Toga is a wrapper around native system calls, so you have a common interface to generate native system widgets. However, you still have access to all of the platform internals if you want them, so you can drop down to a completely native API call anywhere you need to. So here's a bit of a taster of what it looks like in practice. You define an application that extends the base Toga.app class. Startup method says we're going to build this application. In this case, we're going to have a list widget. When you swipe to delete an item on the list, the remove entry callback will be invoked. The startup method also describes a container that's going to hold the list. We set the main window for the app to be this container. This top-level container is going to have an action on it. It's going to have a button in the top right-hand corner. When that button is pressed, we want to show a dialog. The AddItemDialog is a container that holds the input widget, and the bit you can't see here, because it's using system defaults, is that the layout of the container is driven here by CSS. So I could, for example, put a little bit of extra padding around the input if I wanted to match styles, the style guide for the application or the platform. The dialog has an accept and a cancel action. When it's accepted, add entry will be invoked. And lastly, we define some callbacks. We show an add dialog. When we show the add dialog, we clear the input as well. You add an entry, you get the value of the input, add a new list entry with that text and clear it, remove, refresh, follow a similar pattern. And that's it. If you want to see this in action, I've got a link here to a video of a full version of this app running in iOS, simulator in the movie, but it does also work on device as well, and Android. And for bonus points, almost exactly the same code for running a single-page web application, which means Python code running in the browser, utilizing a user interface declared entirely in Python, no JavaScript required. I'm talking about that tomorrow. 1 or 1.25 source code bases, 3 apps, all platform native. And that page actually has links to the source code as well. The last piece of the puzzle is making it easy to take this generic Python project and turn it into a working iOS or Android project. That's where Briefcase comes in. I've spoken previously about using cookie cutter to generate stub projects. Briefcase is a setup tools extension that uses cookie cutter and the project metadata from setup.py to generate ready-to-compile iOS projects. And it's basically as simple as saying pip install Briefcase, Python setup.py iOS, Python setup.py Android, and it spits out a working app. So, what does the future hold? Well, there's still a lot of work to be done. I intend to keep working on Rubicon, Vaak, and Toga. Collectively, these tools make up the BeeWare project. If anything I've spoken about today sounds interesting, you'd like to help, I'm around. And anyone who does contribute, thanks to MaxCDN, can get one of these shiny little challenge coins. Some people think that what I've been doing for the last couple of years is tilting at windmills, and maybe they're right. But I think that as a language community, we've got a huge threat on our hands. Mobile as a platform is starting to get really important in the development landscape. And if Python doesn't have a good story on mobile, we run the risk of being left behind. And that'd make me really sad, because we've built something really great here in Python, a language that's accessible to newcomers, robust enough for professionals, useful in multiple domains with a great community spirit. But the threat is also an opportunity. In short, I think, like any great Dickens novel, the tale of two cell phones is just getting started. It's the best of times, the worst of times, the age of wisdom, the age of foolishness, the epoch of belief, the epoch of incredulity. Details, that's my details there, my Twitter handle, and pybe.org for any more details if you want to look up into the projects I've been talking about. Thank you. Unfortunately, apparently we've run out of time for questions, so I will be out in the lobby if anybody wants to talk to me. I'm also available for hire, and I want to fundle his PyB work, so if anybody wants to come and, throw jobs at me, fine, I'm okay with that.